So the next concept we're going to look at is the concept of symmetry. A symmetry of an object is a rigid motion that moves the object back onto itself. So there are in symmetries, if we have two dimensions that we're moving in, you only have rotation and reflection. A translation would not give you a symmetry because it moves the object. So you wouldn't actually have a translation symmetry. So we're just looking at rotations and reflections. There are two types of symmetries. We have a D-type symmetry, and that is where an object has both reflection and rotation symmetries. The reason it's called a D-type is because a D actually has rotation. If you rotated the D around 180 degrees, 360 degrees, it would look exactly like itself. If you reflected it horizontally through this line right here, it would actually have a reflection symmetry. So that's why we use the D for the D-type symmetry. And then normally we put a little n down here, and that says how many reflections and rotations it has. It will always have the same number of reflections as rotations. So if something is a D2, that means it has 2 reflections and 2 rotations that will bring it back to itself. So those are types of symmetries. The other type of symmetry is a Z-type symmetry. A Z-type symmetry is one that has only rotational symmetry. So the reason we use a Z is if you rotate the Z 360 degrees, it would look like itself, and there are no reflection symmetries. So that's why we use the Z. That might help you remember is it D or Z. Think of the letter of what kind of symmetry it has. And again, it has an N down here as a subscript, and that is the number of rotational symmetries it has. So let's look at some objects and figure out what kind of symmetries it might have. So let's look at this square. If I were to take this square and do a reflection down between these two corners and reflect it about that line, it would look exactly like itself. If I did it about these these corners, this line here with this corner, it would look exactly like itself. If I went through this horizontal center here, drew a horizontal line, and flipped it, it would look exactly like itself. And I did the same thing with this vertical, it would look exactly like itself. If I also pick it up and rotate it, like that corner, took that corner and rotated here, rotated about the center, so that corner came over here, it would look exactly like itself. If I took this corner, instead of going only 90 degrees, I went 180 degrees, again it would look like itself. I could rotate 270 degrees, it would look exactly like itself, or I could rotate it 360 degrees and it would look exactly like itself. So it has 4 reflection symmetries and 4 rotational symmetries. Notice it doesn't have any other symmetries. If I tried to rotate it at any other angle, or I tried to reflect it along any other lines, it wouldn't look like itself. So they're the only symmetries it has. The thing to notice is that there are 360 degrees usually in a total rotation. I shouldn't say usually, always. And there are 4 corners, 4 sides to a square. And if you divide 4 into 360, it gives you 90. And notice I mentioned we had 90 degrees, 180, 270, and 360 as our rotations. Since this has both reflective and rotational symmetries, it's a type D, because D again is for rotation and reflection. And there's 4 of them because it has 4 reflections and 4 rotations. So it's a D4. This propeller, if I were trying to reflect about it, let's say I try to reflect about this line here, it wouldn't look like itself. It'd be something a little off. If I tried to rotate about here, it wouldn't look like itself, it'd be something off. So there are no reflective symmetries. Rotating wise, if I were to rotate about the center, I would get to here and it would look like itself. And I can do that 1, 2, 3, 4. 4 times I can do that. Again, that means I've got 90 degrees, 180, 270, and 360, because 360 divided by 4 is 90. Since it only has reflective and not rotational, since it only has rotation and not reflection, it's a Z. So since it has 4 of them, this is a Z4. Let's look at a rectangle. If I were to draw a line directly through the center, vertically this way, and flipped it across that line, rotated, reflected across that line, it would look like itself. If I did the same thing with this line, this horizontal line, again, it would look just like itself. So it has 2 reflective symmetries, And then if I were to take this corner and rotate it all the way over to here, or took this corner and rotated it all the way around, meant we went either 180 degrees or 360 degrees, we have 2 rotations. Again, think of it as we have 2 places, 2 divided into 360 is 180. So we have 180 and 360. It is a type D2 because it has both reflective and rotation. And there's only 2 of them, so that's where the subgroup 2 comes from. I'm looking at this triangle. I can think of having, if I drew a line through this is an equilateral triangle, and if I drew a line through this one side and through that vertex, I would have reflective. Same thing with this one, same thing with this one. There are therefore 3 reflective symmetries, which means there should be 3 rotational. And there's 1, 2, all the way around is 3. And 360 divided by 3 means that each angle I went 120 degrees, I went 240 degrees, or I went 360 degrees. Since there's both reflective and rotation, this is a D, and since there's 3 of them, it's a D3 type. Isosceles triangles don't have as much reflective. If I went from here down, isosceles triangle means that 2 sides are the same. And if I went through this reflective, I would have looked like itself. And if I rotated 360 degrees only one time, it would look like itself. So that it has both reflective and rotation, so it's a D, and it only has 1, so it's a D1. The scalene triangle, which means none of the sides are the same length, there's no reflective symmetries. No matter where I drew a line, I wouldn't look like itself. It does have rotational. If I went from here all the way around and back to where I started, that's 360 degrees. So it only has a rotational symmetry, which makes it a Z, and it only has 1 of them, so it's a Z1. You can do this with lots of these different ones. If I took this 5-sided figure and worked with this one, I would notice I have 1, 2, 3, 4, 5 reflective symmetries, and I would therefore also have 1, 2, 3, 4, and 5. 360 divided by 5 is 72, so I'm going to have a 72 degree angle. Add 72 and 72, you get 144, then 216, 285, and 360. Since there are 5, there's both reflective and rotational, it's a D, and since it has 5 reflections and 5 rotations, it's a D5. As a reminder, it always has the same number of reflections as it has rotations. If you have 5 rotations, you better find 5 reflections. If you find 5 reflections, you better find 5 rotations. This petal, again, if I were to draw a line through here, one side would look like itself, same thing here, and I can do that 5 different times, and then I can rotate around. This is a lot like the pentagon up here, so we go 5 times around, and we'd have a D5 because it's 5 rotations and 5 reflections. This one has no reflective symmetries. This sandwich, but the sandwich does have a rotational one, mainly going around 360 degrees. So it's a Z because it only has rotation, and it's 1 because it only has 1. The letter A, if I do a vertical line down through A through the center, I get a reflective, and if I went 360 degrees all the way around, I would also have a rotation. And so we have a reflection and a rotation, makes it a D, and there's only 1 of them, so it's a D1. The S, on the other hand, has no reflective symmetries, because if you draw the line through here, the S would be backwards. Think of it as you draw a backwards E, a backwards S. So it has no reflective symmetries. However, with rotation, I can take that S, turn it 180 degrees, it looks just like itself. I do it again and do it 360 degrees, it looks just like itself. So it has 2 rotations, no reflections. It has no reflections and a rotation. It's a Z, and there are 2 of them. So it's a Z2. The letter Q, again, has no reflective symmetries. No matter where you try to draw a line, it would look different. And if you rotated it, the only way it would look back to itself is if you rotated 360 degrees all the way around. And so it only has the one rotation. Since it only has rotation and not reflection, it's a Z. This is Z1 because it only has one. The letter O, on the other hand, you can actually draw a reflective symmetry, reflective line through a whole bunch of different ways. And I can rotate through any angle I want. So we call that a D infinity because it has an infinite number of reflections and rotations it can have.